So we see a lot of excitement, right? We see countries and companies spending billions of dollars on AI. And this is an extraordinary time to be in this field. I've been in the field now, I guess I wrote my first AI program, well, it's too long ago to mention, well before I was born, 42 years ago. And I've never seen anything like the level of attention from governments, from financiers, and even the stodgy old British government has got excited and is deciding to spend very significant quantities of money on this field. So, for various reasons, I'm not going to go too much into the technical side of what's happening with the research progress in AI. But I think it's prudent to assume that at some point, and I don't want to say when, at some point we're going to have AI systems that are substantially more intelligent than humans, meaning that in real-world situations, not in games, not in stock trading, but in ordinary real-world situations, AI systems will make better decisions than humans. They will have access to much more information than any human can possibly process, and they will be able to look further ahead into the future, far further ahead with greater accuracy than we can. So, there's a reason why all those countries and companies are spending billions of dollars on AI. It's because if we succeed in this goal, then that will dramatically change our civilization forever. I think it's reasonable to say that this would be the biggest event in human history. And we can have a far better civilization in future than we have now. And if you just take, I would say, what could be a very modest goal, with this technology, we could raise the living standards of everyone on Earth so that even a Parisian would find them acceptable. And when you calculate what that does to the GDP, it's about a 8 to 10-fold increase in the GDP of the world. And that translates into $10,000 trillion in net present value. So that is the reason why these countries and companies are investing. In fact, when you consider the size of that prize, billions of dollars seems actually a tiny amount of money. And I would say that at the moment, progress in AI is not limited by money at all. It's actually just limited by the availability of brains that can solve some of the hard problems that we still have to solve. So, I think with any powerful technology, there are going to be some downsides, and we're already seeing some of those. For example, the use of AI to kill people is quite popular with some of the governments around the world who are developing autonomous weapons. And I've been quite involved in trying to convince governments not to go down this route because autonomous weapons constitute weapons of mass destruction. And they constitute weapons of mass destruction because they're autonomous. Because they're autonomous, they don't need human supervision. So theoretically, one human being can launch 100 million weapons simply by writing a little program for I equals 1 to 100 million do. Go find someone and kill them, right? And so whether we'll succeed in this, I don't know. But if anyone is interested in working on this effort, you can go to autonomousweapons.org and find information, find there are groups you can join. And I'm, at the moment, a little bit disappointed with the French government, which is actually not exactly helping push a treaty forward. They are asking for a vague political declaration that yeah, humans should be involved somehow, but they are falling well short of actually supporting the treaty, unlike China, for example. So, interesting situation. People talk about AI eliminating employment in many industries, and I think this is a real concern. Probably of all the policy concerns for governments, this is the biggest one right now, because it's going to require very significant changes in the structure of our economy and of our education system and of our scientific research base in order to have an economy that you or possibly your children would actually want to live in. Because most of what we currently think of as work is probably going to be done by machines. But this is what I want to actually talk about today, the end of the world. So, why is AI possibly going to be the end of the world? So I've been thinking about how we got ourselves into this situation. Right? What is the nature of the problem with making more capable AI that leads it to have such potentially negative consequences for humanity? When you look at what the definition of AI is and has been, it's based on the definition of intelligence for humans. And generally speaking, when we talk about intelligence, we talk about rationality, we talk about decision-making. And in English, we would say that humans are intelligent to the extent that their actions can be expected to achieve their objectives. I should say our objectives. Right? Our actions can be expected to achieve our objectives. And so the natural thing to do is to say, all right, we want to do AI, we want intelligent machines, so we'll just translate this definition and replace humans with machines. And then we have machines are intelligent to the extent that their actions can be expected to achieve their objectives. And this definition actually is pretty common to a lot of fields, not just AI, but control theory. You are always minimizing a cost function J. In economics, you're maximizing a utility U. In operations research, you're maximizing a sum of rewards R. In statistics, you're minimizing a loss L. And so all these fields share essentially a common definition of what they're trying to do. And then where does this objective come from? Well, people just put it in, right? The field of AI, the field of control theory has nothing to say about what the objective should be. Right? It's simply up to the human to stick in the objective and away we go. And the problem with that is that if you put the wrong objective in and your machine is sufficiently intelligent, then you can have all kinds of disastrous consequences. Right? So we call this the King Midas problem. So King Midas said, I have the objective that everything I touch should turn to gold. And his objective was put into the machine. Basically, the gods granted him his wish. And then, of course, his food and his drink and his family turned to gold. And he died in misery and starvation. So this is an old, old story. The story of the genie who grants you 3 wishes, and your third wish is always, please undo the first 2 wishes, because I made a mistake in specifying those wishes. It is extremely hard to specify objectives correctly when you have machines that are really intelligent and capable of functioning in the real world. Right? It's one thing to say, okay, the machine is confined to a virtual Go board or a virtual chessboard. And in that virtual Go board or chessboard, the only thing it can do is to print moves on the screen, and so we'll just specify the objective to win the game, right? But imagine that Go program was actually a little bit more intelligent, right? And could do things like bribe the referee, change the programming on the Go board simulator to actually simply eliminate some of the opponent's pieces from time to time. right? Or pay someone to poison the opponent, or and these are things that chess players have actually done in the real world in order to win tournaments. And so just specifying, win the Go game is an extremely dangerous objective if you have a machine that is sufficiently intelligent. And if you say things like cure cancer, well, then you're really in trouble, right? Because the fastest way to cure cancer is probably to, first of all, induce tumors in the entire human population, probably multiple tumors, because that way you get to run more experiments. And then try millions of experiments with millions of treatments to come up with something that cures cancer. So, these are just signs that we got something wrong, right? That we actually don't want machines that are intelligent. And so, arguably, we made a bit of a mistake in setting up the field in the first place. So what we do want, I think, is machines that are beneficial, right? Whose actions can be expected to achieve our objectives. Not their objectives, not objectives that we put into them, but our actual objectives. And the key thing is that our objectives are within us, right? They are our preferences about what future life we would like to have. And they're not in the machine. And so this is a different formulation of the problem, and I believe this is in fact the correct formulation of the problem. And it leads to a quite different technological development. Right? The research agenda looks very different from the traditional research agenda of AI. And so what I'm trying to do with this research agenda is to develop the technology to have provably beneficial machines. Because when you're producing something that is potentially much more intelligent than humans, it's not enough to say, well, we've tried hard to make it safe. Right? We need mathematical guarantees. We need the machines to be constitutionally incapable of acting in ways that are contrary to our interests and preferences. So that's what I'm trying to do, and I'll explain a little bit more about how this is going to work. So in the nutshell, right, and I chose 3 because of Asimov's laws, right? There are 3 Asimov's laws, and I think, he was sort of in the right ballpark, but he was missing a few important things. So the first principle is that, as I said, that what the machine is supposed to be doing is maximizing human preferences. But the machine does this uncertainty. This is the new element, and it turns out to be crucial because it causes machines to defer to humans in a way that a machine that believes it knows what the objective is will not defer to humans. Because in fact, once the machine has the objective, humans are completely irrelevant. It doesn't matter what they say, it doesn't matter what they do. The machine is pursuing the objective, and that's that. So, these two by themselves are not quite enough, because you need a way to actually ground, right? So the robot is uncertain about some hidden variable that's inside the human. There has to be some connection between that hidden variable and what the robot perceives in the world in order for it to actually learn about our preferences. And the connection is really human behavior, right? This is the defining ground truth of what our preferences are, but I put an asterisk here because it's actually much more complicated than that, right? Our behavior does reflect our preferences, but it's mediated by an extremely complicated cognitive architecture that humans have, which is far from being rational. And this is the biggest scientific problem that we face here. In addition to the mathematical problems of defining algorithms and proving theorems, there's a scientific problem of understanding enough about the nature of human cognition to allow the machines to invert human behavior to access human preferences. Okay, so those are the three ideas, and if you're familiar with graphical models, this is a little picture of what's going on. If you're not familiar with it, it's still pretty intuitive, I think, right? So, so AMA is the name of my textbook. So this is the first 3 editions of the textbook. We define AI as coming up with a machine behavior that optimizes some objective that the human puts in, and we assume that the objective is directly observed by the machine. So in graphical models, when a variable is directly observed, it's filled in. We know the value of that variable. And so what that means is that once the human objective is observed, the human behavior becomes irrelevant, right? The machine doesn't care anymore about what the human is doing, even if the human is jumping up and down and saying, no, 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 please don't do that, please don't do that. The machine doesn't care, because the machine believes it's observed what the human objective is, and whatever actions it's taken are rational in its eyes in pursuit of the human objective. And this is just a simple mistake, but it's been embedded in the field now for more than 50 years. Now, in graphical models, if the human objective is unobserved, then the human behavior and the machine behavior are actually mathematically coupled to each other. So, because the human behavior continues to provide information about the true human objective. And that's the important difference, right? So now it matters what the human being does, because that provides more information about human objective, and the whole goal of the machine behavior is to optimize the true human objective. And so, from a sort of societal point of view, it means that machines are going to be coupled to us in this intimate way of needing to observe our behavior, to understand our preferences, to work with us, and to defer to us in order to help achieve our objectives. From a mathematical point of view, it makes things much, much, much more complicated. Because now, instead of having what is usually a single agent decision problem, where you just choose a course of action that optimizes expected value, you now have what economists call a game, right? Which means a decision problem involving more than one decision-making entity. Because now, right, the human is part of this game as well as the machine, and they have to adjust behavior to each other. For example, the human now has an obligation to teach the machine, right, by taking actions that make it clear or more clear to the machine what the human wants. And the machine interprets human behavior in the light of this coupling and understands that the human might be trying to teach them something. And so on. So this game theory is much, much more complicated than single-agent decision-making. And it's, I would say, a less developed field because it lacks unique solutions. Right? So when we look at game theory and calculate Nash equilibria, we often find that there are multiple equilibria. There are multiple solutions where both parties to the game believe they have no incentive to deviate from that solution. And so it's just much, much more complicated. But this is the problem we have to solve, so we just have to live with that. Okay. So let me give some concrete examples. I don't actually know the background of everyone in the room. I guess it's very diverse. But you know, if you worked at all with machine learning, you are probably quite familiar with what I'm about to tell you. So in image classification, right, the classical way that you train something that recognizes objects in photographs is to provide it with lots and lots of photographs with labels for each one. This is a dog, this is a cat, this is a Citroen, this is a Peugeot, and then you just have 40 million of those, and you pass it to a learning algorithm. The learning algorithm learns to recognize the kinds of objects that you see in those photos. And So the objective function that you pass into the machine is usually it's minimize a loss function, right? This is standard statistical learning, and the loss function is expressed using what's called the loss matrix, right? Which says what is the cost of misclassifying an object of type A as an object of type B? So what's the cost of misclassifying a dog as a cat or a Peugeot as a Citroen? And almost invariably, when people do machine learning, they forget that part of the problem, right? They just leave out the loss matrix, which is equivalent to saying that the cost of misclassification is the same for every two kinds of objects, right? And this is what Google did in its image classification system, which you can use to label your photographs, to find things in pictures, and then do search to find pictures of those kinds of objects. And so then what happened is Google accidentally classified a human being as a gorilla, and then this was posted on Twitter and Facebook and everything else, and got umpteen thousand million views, and Google faced a huge public relations disaster. Now, if they had thought about what their actual objective function was, they would have realized that the cost of misclassifying a human as a gorilla is about 1 million times more than the cost of misclassifying a dog as a cat. But they never even thought about it, right? They just ran standard machine learning algorithms with effectively a uniform loss matrix. So that caused them to have a lot of grief. Now, if they were honest, they would have said, okay, well, we should think about this loss matrix, but in fact, we don't really know what it is. We can give you some qualitative guidelines on what it might look like, but it's a big thing, right? If you're classifying, as we do in ImageNet, there's more than 20,000 categories of objects. So you're talking about a matrix with 400 million entries. And the idea that you could just pay someone to fill in 400 million numbers and that would be the right answer is probably not going to work. So you're going to have actually uncertainty about what the loss matrix is, and then you're going to have to find ways of specifying that uncertainty in terms of some complex structured prior over the contents of the matrix. So it's a 400 million dimensional probability distribution, and then you say, okay, well, what textbook should I read to find out how to do this? And the answer is there isn't one. Right? This problem has not really been studied. But obviously it needs to be studied. And you see this over and over again, right? Because all these fields assume that the loss function, the objective function, the cost function is fixed and known, and it just isn't true in the real world. So if you have a machine that's uncertain about the loss matrix, then it's quite reasonable for the machine to say, I don't think it's safe to classify this object at all. Right? I'm going to refuse. I'm going to refer you back to the human and say, ask that person, or go ask Google what this photograph is. And the system can use what we call active learning techniques to actually gain more information. It can say, is it safer to classify this object or to leave it unclassified? Is it safer to take these two, for these two photographs, is it okay to make a mistake, whereas with these other two photographs, is that not okay to make a mistake? If you get more feedback of that kind, you can pin down more about the loss matrix to the point where you have a system that would actually then be safe to deploy in the real world. But this is an entirely new methodology for machine learning that does not exist, and it needs to exist. Okay. Sorry. Another example, which is probably familiar to everyone, you ask someone to fetch a cup of coffee. Right? Well, what that means to a human being is actually an extremely complicated thing. Right? It does not mean, okay, your life's mission is to forget everything else you ever cared about and get me coffee. That's the only thing that matters in your life. Right? That's not what it means, but that's the way we've been using it in programming robots. Right? it's entirely reasonable for the other human being to say, oh, you know, they're out of coffee at the bar, you know, do you want me to go out and find another cafe and bring some back, which will take 25 minutes, or do you want to just pass? Or we're in the middle of the desert, the nearest coffee is 500 miles away. Do you really mean go fetch the coffee? Or they might just say go fetch the coffee yourself, right, because they're too busy. So go fetch the coffee is not an instruction. It's simply conveying some information that all other things being equal, I would be a little happier if I had coffee than if I didn't have coffee. Okay? Now that all other things being equal is very helpful for the machine. Because even if it doesn't know, for example, whether you care about paying €1,000 for a cup of coffee. Right? So it doesn't know you want coffee, but doesn't know your relative preference between coffee and money. Doesn't know your relative preference between coffee and time. If the robot can find a way of getting coffee without changing any other part of the world, then it's still safe for the robot to get you the coffee. So what this tells you is that in the face of even very great deal of ignorance about human preferences, minimally invasive solutions are still safe for robots to carry out, and that's exactly what we want to have happen. A third example, right? We would like robots to let us switch them off. Seems reasonable, okay? But if you're a sufficiently intelligent robot and you have a mission to fetch the coffee, right? Then of course you know that when you're switched off, you're not going to be able to fetch the coffee. It's just straightforward common sense. And so by giving a fixed objective to the machine, you've actually given it an incentive to stay alive, to defend itself against any attempt to switch it off. Right? So it's just a logical consequence. It's not that we're building in self-preservation to the machine, which Asimov recommended. It's his third law. There's no need to do that at all. For almost any objective that you give a machine, the machine has a derived incentive to stay alive in order to carry out the objective. And so, so the first thing that the robot would do would be to disable its off switch, right? And possibly even take preemptive steps against anyone who might interfere with the mission of getting the coffee. Now, if we look at a machine that is uncertain about the objective, we'll see that it will allow us to switch it off. It will defer to the human decision because it's uncertain about what the human really wants. So let me just give you a very simple derivation of that result using a trivial example. Okay, so in this example, the robot has a choice, okay, at the beginning. And the robot can choose some action which may be risky for the human, right? So it may have some possibly serious negative consequences for the human. Now the robot does not know what the human preferences are. And so it's very uncertain about what the utility of this action is. So I've indicated that by, so I've indicated that by this distribution, and you can see the distribution has a slightly positive expectation. And so the robot says, okay, this, at least as far as I know, this action is beneficial to the human, but it could be really bad. Okay. So the next choice the machine has is to switch itself off. Right? And that will fix the utility of switching itself off at 0. Okay? So the action of just doing this risky action, this is equivalent to disabling your off switch, right? Because you're not giving the human any possibility to interfere. Okay? But you could just commit suicide. And if the robot thought that the expected value of this action was a little bit negative, then if these were the only two choices, the robot would commit suicide, which is also not good. Right? So we're going to give the robot a third choice, which is to wait, and then give the human the option to switch off the robot. Okay. So this means not disabling the off switch and allowing and telling the human, okay, this is the action that I want to do, giving the human a choice to switch off the robot. Okay. So now the human can switch the robot off, which has value 0, or the human can say, go ahead. So if the human says go ahead, what does the robot know? Right? The robot now knows that the value of this action is non-negative. Right? Because if the value of the action was negative, the human would have switched me off. Okay? And so, at that point, the robot can act, and now the distribution of the value of this action is non-negative. So all that part of the distribution where there was a risk to the human has disappeared, because if there was a risk to the human would have said, no, don't do this, I'm going to switch you off. Okay? So now the robot is safe to take this action, and so the robot has an incentive to follow this path where it gives the human a choice to switch it off, because it can then end up either here, where it has positive value, or here, where it has value 0, in the case where the action is actually risky to the human. So because what the robot is trying to do is to optimize value for the human, this gives the robot an incentive to allow itself to be switched off, right? To defer to the human, rather than just choosing the action that it believes maximizes expected utility. And so you can also see that as this distribution becomes more and more narrow, in fact, the incentive to allow the human to switch you off disappears. So the more certain the robot is about the objective, the less willing it is to be switched off. Okay? And that's a simple mathematical relationship. So what we want to have happen, actually, is that the robot only achieves certainty about the objective when it is correct about the objective. Right? And that can be done using Bayesian learning from observations of human behavior, and assuming that you have a correct model of human cognition that produces that behavior from preferences. So there's a long way to go to guarantee that, but this, it seems to me, is at the core of how we make AI safe, by making sure that the machines are uncertain about the objective. And you can show very straightforwardly that this kind of design gives you machines that are provably beneficial. So you're better off with this kind of machine than without it. Okay. So now let me talk about the complicated part, right? The difficult part is human beings themselves. Right? If we were rational, then this would be straightforward, right? But we're just not. The technique of learning from human behavior, learning what the preference function is from behavior, has actually been studied for quite a long time. There's a field called inverse reinforcement learning. And it's called inverse reinforcement learning because reinforcement learning means, given a reward function, figure out an optimal behavior. So this is how AlphaGo learns. The reward function is +1 if it wins, -1 if it loses. So it plays itself lots of times and it learns to win, right? So that's the reinforcement learning process, because the reward function is given and then the goal is to find the optimal behavior. This is the inverse of that. We're observing human behavior and then we want to figure out what is, or the machine wants to figure out what is the reward function or preference function being optimized by this behavior. Need to make that a little bit more complicated because, as I said, this is really a coupled situation. So it's not that the robot is observing the human like through a two-way mirror, and the human is unaware that the robot exists and is just going about human business. In fact, the human and the robot are in the same world. The human knows that the robot is watching and learning. The robot knows that the human knows that the robot is watching and learning. So the robot expects the human to do teaching kinds of things, not just doing. Right? So imagine that the robot is learning to be a surgeon, and the human is the expert surgeon. Right? Well, the human's not just going to go about doing the surgery without any commentary, without sort of showing, right? They're going to say, look, okay, I'm just opening this part here of the skin, and I don't cut too deep, because if I cut too deep, I'm going to do this, and well, let me show you what happens if you make this kind of mistake and how you fix it, right? They're gonna do things in a way that is sort of robot aware, right? Knowing that the robot is watching, and therefore doing things in a way that is pedagogical rather than just optimal from the point of view of surgical efficiency. And so in order to understand the human behavior, the robot needs to know that, right? The robot needs to know that the human is going to be sort of doing teachy behavior and not just optimal problem-solving behavior. So in the cooperative inverse reinforcement learning, it's a two-player game, right? So there's the human and the robot, and in the basic game, there's just those two things, right? So if you like, you can imagine that this is the whole human race, and this is all the machines, right? But we'll imagine them as being single agents. So the human has some unknown preferences, and we'll call those theta, right? And the human acts, we'll say, roughly according to theta, right? So not perfectly, but there is some consistent connection between what human preferences are and the actions that humans choose. And then the robot's goal is to maximize this theta for the human without knowing what it is. Okay, but the robot has some prior belief, which we call P of theta, about what the human preferences are. Okay, and when you set things up this way, you can actually solve the games, as long as it's not too complicated. And you can calculate what the equilibria are, the Nash equilibria of these games. And indeed, you find that in the Nash equilibrium, the human is teaching the robot. And the robot is deferring to the human and sometimes asking questions. And as I said, allowing itself to be switched off. So you get these really interesting behavioral dynamics by solving these games. And these kinds of behaviors are just inaccessible to classical AI, right? Because they can only be produced because the machine is uncertain about the objective. Okay, so I'm going to skip over this. There's a lot of technical papers. You can read them if you are interested in that kind of stuff. So this is where all the mathematics is, the algorithm design for how you solve these games efficiently. So I'm not going to go into any more detail on those. So I want to talk about a couple of objections that have already been published to these ideas, which I actually think these objections really just validate the ideas. Of course, I always think that. Right? So one is, well, what if the machine's prior actually rules out the true preferences that the human has? Then doesn't that mean that the robot can never learn what the human preferences are and will then not be safe? And I think this is a reasonable challenge in the sense that the machine has to allow for, shall we call them, unknown unknowns, right? There are things that humans actually care about that it never even occurred to humans to think that they cared about because they never occurred in the real world at all. But in the world that can be shaped by AI, right, by arbitrarily intelligent machines, things will happen that have never happened before, right? And there are possibilities for how things could go. For example, if you think about the Matrix, right? Probably never occurred to you that in fact the entire human race could be put into vats, with wires connected into their brains that give them simulated experience so that they think that they're in the cafe of the bureau listening to a lecture by Stuart Russell, whereas in fact they're just brains in vats, right? You probably never thought of that, but but the machine would need to know that people might have a view on that, but they've never expressed it. They've never written anything down about it. They never behaved in a way that indicated a preference one way or the other. But of course, if we actually brought it up, most people say, no, we don't want to be in the Matrix. Well, tough you are, sorry. So we don't want to be in the matrix, and so this is an unknown unknown, where the machine has to allow for us to have preferences about things that that it doesn't even know exist, and we don't know exist. So this is a reasonable question, and in fact we know how to write prior distributions that are universal in the sense that they can accommodate any possible actual set of preferences that a human could have. It's just that when you write universal priors, you end up learning slowly. You need a lot more information to narrow down a universal prior to the point where it's useful. So a second objection is that if humans are not rational, then you've got two things to find out, right? Sorry, there's a bit more math in this than I remembered. So the actions that the human produces, A, are some function f of the human preferences theta, right? And if both f and theta are unknown, right? If you don't know how it is that humans produce actions and you don't know what their preferences are, then it's impossible to identify both of those things simultaneously, right? And to some extent that's true, but in fact, so let me illustrate what that means, right? So let's take Garry Kasparov, world chess champion. Right? Now, it's theoretically possible that in fact Garry Kasparov is so irrational in his choice of actions that even though he wants to lose every game of chess, he fails to lose every game of chess. He keeps winning, right? So he's sort of anti-rational, right? His way of producing actions is the exact opposite of rationality, right? Now that's theoretically possible. That's and that's what's going on, right? And then he feels inside, damn, I won again, right? But his ability, right? But he keeps saying, yes, I'm so happy that I've won, right? Even though he isn't, right? So I mean, yes, so mathematically that's possible, but a philosopher would say this is just a basic philosophical mistake, right? If you are anti-rational, then those are not your preferences, right? If you want to lose, and you see a move which guarantees losing, and you choose the exact opposite move, right? Then you didn't really want to lose at all, right? It's meaningless, in fact, to say that you act in exactly opposite of your own preferences, because then they're not your preferences at all. Okay, and so you have to have some constraints. So even though humans are not rational, their ability to produce behavior there has to be some constraints on the relationship between preferences and behavior for them even to count as preferences, right? And in particular, if there's an action that satisfies your preferences, then it's reasonable to expect that you would take it most of the time. Okay, so these are interesting objections. I think I'm going to skip over these ones, actually, and talk about some of the extensions of this work that we're currently interested in. So one of those is what happens when there's more than one input. Okay, so a lot of people ask, well, whose values are you going to put into the robot? Right, so that's wrong on two counts. Number one, we're not putting values in the robot. That's the whole point. Right? We're not putting any values in the robot. And number two, the robot's job is actually not to find one ideal set of values or one ideal set of human preferences, but just to find out what your preferences are. Right? So all 7.4 billion of you, or of us, you could have a machine learning 7.4 billion preference models. Now, the second question is, well, how do you deal with the fact that you can't satisfy all those preferences simultaneously? So if everyone wants to be king of the world or queen of the world, they can't all be king and queen of the world, right? So what do you do? Now, it turns out that there is a famous theorem by Hassani, who was an economics professor at Berkeley, Nobel Prize winner, and his theorem said that the only solutions are ones that represent linear combinations of the preferences of the people that you're making decisions on behalf of, right? And that theorem requires that all the humans involved have exactly the same beliefs about the world, which is actually pretty hard to guarantee. And so Andrew Critch, who's in my group, started thinking about this, and he said, okay, well, what happens if the humans have different beliefs? So then, interestingly, it turns out that optimal solutions are no longer fixed linear combinations of the preferences of the individuals. The weights in the linear combination actually change over time as you find out whose beliefs are more in agreement with reality. So someone who, so this is a classic example if you have children, right? So one child wants to go to the beach, the other child wants to go to the movies. So, of course, the one who wants to go to the beach believes that it's going to be sunny tomorrow. And the one who wants to go to the movies believes that it's going to rain tomorrow. This is what we call motivated cognition. Okay? So, fortunately, in this situation, you can make a deal. Right? You can say, fine, if it rains tomorrow, we're going to the movies, and if it's sunny tomorrow, we're going to the beach. Right now, both children are happy because they both think they're going to get what they want, so they will agree to this contract. But this is not a contract that Harsanyi's theorem could produce. You can only take linear combinations. You can't have this sort of conditional thing where the decision that gets made changes based on what gets observed in the world. But Critch's theorem shows that, in fact, you can have this kind of conditional contract, and it falls out very naturally as a result of this fact that you pay attention to the preferences of the person whose beliefs turn out to be correct. So that's a very interesting first step towards how we optimize things on behalf of multiple people. There are some other interesting questions that come up, and I think these are actually very relevant to the general aims of effective altruism, because they are real issues about what we call welfare aggregation. Right? So the classical utilitarian view of the world is that you basically add everything up, right? And unless you're a royalist, you believe that everyone's preferences count equally, okay? Now, you can't add up preferences unless they are on some commensurable scale, right? They have to be measured on the same scale in order to add them up. And Nozick pointed out that there are things called, or there could be things called utility monsters. Actually, I know there are things because I have children who are utility monsters. So a utility monster is someone whose preferences are just much, much, much more extreme than those of ordinary humans, right? So, you know, ordinary humans walking along and it starts to rain a little bit. He said, oh, that's a nuisance, you know, that's okay, I only got a couple hundred yards to go before I'm home. Right? Utility monsters, like, this is horrible, I can't stand it, I can't stand the rain. Right? You know, and, or the sun comes out and you smile because the sun's out and the utility monster is jumping up and down for joy and the weather is fantastic, it's lovely, what a wonderful world this is. Right, so they're just on a scale which is much, much, much more extended than the preferences of ordinary people. And so Nozick pointed out that this is a fundamental difficulty for utilitarians, right? Because if you're adding up preferences, then you need to give 100 times as much weight to this guy because he just has really, really extreme preferences, and that's the way it is. And it doesn't seem fair or right somehow, but at the same time, you know, we are all utility monsters relative to the table. Right? The table doesn't really care if it gets rained on or if the sun comes out. Right? And that's why we pay no attention to its preferences because they're completely flat. Right? Relative to the table, we are the utility monsters. We're the ones with the extreme preferences. And so, of course, we pay attention to our preferences and not the tables. Right? We don't count tables when we're adding up you know, the satisfaction that we're generating in the world. And so I don't have a good answer to this question. I actually think that there probably is a way to to tease out the extent to which a utility monster is really suffering or really happy by coming up with a way, some kind of common currency that you could use, which I'm thinking might be like time, right? So how does a utility monster trade time for experiences, for rain or sunshine, versus how an ordinary person trades those things? Because we all have the same amount of time. And so there may be some way we can get around this, but this is at the moment an open problem. Another interesting problem is the Somalia problem, which again is very relevant to effective altruism, right? So if the machines owe an equal amount of loyalty to everyone on Earth, to all humans, and is trying to improve the utility of all humans, then it should, as the effective altruists do, it should put its money in the place where it can do the most good, which means that it immediately goes off to Somalia or wherever people are suffering the most and where you could really save lives, prevent people from starving to death. And it certainly wouldn't be cutting the grass in my back garden or making dinner for my kids or any of the things that I wanted it to do when I bought it, right? Now, so that's a problem, not because it's a bad thing for robots to go to Somalia, but because I would never buy a robot that immediately just went off to Somalia and ignored me completely, right? And so but at the same time, I don't want the robot to be loyal just to me, right? Because then it's going to be a nuisance to everybody else in the world, and it's not going to help someone who has a heart attack at the supermarket because it's too busy doing the shopping for me. And so again, that's not how we want robots to behave. So there has to be, I think, some interesting solution here involving, loyalty probably based on how much you paid for the robot. So a limited degree of loyalty to the owner, but a more general loyalty to the human race. Now, another interesting set of questions comes up when you have multiple humans. You get a classical game theoretic problem, which is that people then lie about their preferences, right? They have incentive, for example, to appear to be much more in pain or much more helpless, to appear to be utility monsters, if you like, in order to get more resources from the robot. So this is what we call strategic behavior, and there are many examples of this in microeconomics and in international relations and all kinds of other areas. And so people work very hard in these fields to figure out protocols that guarantee that people are truth revealing, right? So they have no incentive to do anything other than tell the truth. So if you're familiar with the second price auction, right? The standard auction is that everyone bids. Let's say you're selling a house, everyone bids on the house. Whoever bids the highest buys the house, right? Seems fine. But that actually is not a truth-revealing auction. It becomes a strategic auction. If you do a sealed bid second price auction, where the person who bids the highest pays the second highest bid, not the amount that they bid themselves, but the second highest bid, then you can show that this is a truth-revealing auction. So then people have an incentive to bid exactly what they think the house is worth, and no more and no less. So they don't have to think strategically about what the other guys are going to bid, or should I bid more, should I try to get in with a low bid and hope that everyone else bids lower, or any of those things. There's no incentive to do anything other than just bid what you think the house is worth. So this is what we call welfare optimizing auction design, and it's truth revealing. So can we come up with protocols that allow machines to serve multiple humans without inducing incentives for strategic behavior by the humans? Okay, I think we can skip over that. And then, when you've got many robots, then all kinds of other things come into play. Right? One is that because humans actually share a great deal in the structure of their preferences, what you learn about the preferences of one human will help in predicting the preferences of another. They won't be identical, but they'll still be very useful for other robots. So all the robots should share everything that they learn from trying to help the humans in their household, so that then the whole fleet of robots, as it were, very rapidly approaches a good understanding of human preferences. But then, of course, now that creates strategic incentives for the robots to lie to each other. And again, we need protocols to fix that problem. So there's lots of interesting research to do. And then the other part is what happens with real humans, right? So the theorems we have so far are for rational humans and for humans that are what are called Boltzmann rational, which basically means that they make random mistakes and they make big mistakes less often, but their mistakes are random. And real humans are nothing like this. So we actually need to understand, what are the main things that characterize human behavior and in relation to their underlying preferences. So the first thing to observe about humans is that they are computationally limited. So, when Garry Kasparov lost to Deep Blue in a chess match, right? In each of the games he lost, there was a move beyond which he had no possibility of winning. So he made a move that guaranteed that he was going to lose the game. Why did he do that? Right? Well, if you believe he's rational, then you have to believe that he wanted to lose the game. Right? That he was just fooling you with the first 33 moves, and then on the 34th he just lost the game, and that's that. Right? I don't believe that. I don't believe Garry Kasparov wanted to lose. He wanted to win, but he just was computationally unable to make good moves all the time. Okay? And so to understand his behavior, you've got to understand that he is computationally limited. And if you don't understand that, then you're going to get his preferences wrong. So that's one thing. Another interesting thing is that chess is an area where you can kind of imagine that most of the time people are making pretty good moves, right? If they're really good chess players. The real world is not like that. Right? Almost all the time, what you are doing, what I'm doing, what everyone is doing is nowhere close to the best thing that you could be doing to satisfy your own preferences. Nowhere close. Right? Because, let's face it, in chess, the game is over in 30 or 40 moves. Right? What's a move in the real world? Well, a move in the real world is sending a motor control command to your muscles. So in the real world, right, your life is more like 20 trillion moves. Okay, it's not 30 or 40 moves, it's 20 trillion moves. So you're not close to solving the game of life. Nowhere, not even in the remotest ballpark of solving the game of life. Okay? So, so what are you doing? Right? I think what you're doing most of the time is you're actually you're operating in a multi-level hierarchy of sub-problems or sub-routines. Right? So here I am. I'm giving a talk to a group of effective altruists. Right? So because I'm giving a talk, right, because I'm in that subroutine, I limit myself to choosing words. Right? If I took out my phone and started selling AT&T stock or trading euros for ringgits or something, you think I was insane, right? But that might actually be the optimal thing I ought to be doing right now, or betting on England to lose the World Cup, or something like that, right? So to understand my actions right now, it's no good, solving the game of Stuart Russell's life, for all possible preferences he could have, and then seeing which set of preferences agree with his current behavior, because that wouldn't work, right? To understand my behavior, you want to understand where am I in this subroutine hierarchy? What is this subroutine hierarchy? What is this thing called giving a talk, right? What are all the things that I can choose to do, commit to do? And then within those commitments, what are the choices that I have? What is the preference structure of that sub-game? Right? What is the preference structure for giving a talk? Right? Not what's the preference structure for life. And so this is a completely different thing from what we've been doing so far in reinforcement learning and inverse reinforcement learning. In all the decision sciences, they don't have anything really to say about this, the actual structure of life. And so this is a really important thing to study, and we're calling it hierarchical inverse reinforcement learning, but it's a really interesting problem. But fortunately, right, if we don't solve this kind of thing, we're not going to be able to make super intelligent robots either, right? Because super intelligent robots also, to cope with the complexity of the real world, have to have this kind of hierarchical structure in their behavior, right? So as we make progress on solving the AI problem, we presumably will derive insight about how to solve the inverse of that problem in order to understand human behavior and its structure. Okay. You know, I think I'm at the point where we are going to start working on some real preference models, right? So not toy problems anymore, not just mathematical theorems, but actually building, for example, assistants to humans that maybe help you with your travel, your calendar. So all the kinds of things that a human assistant would do for a person, but have a machine that does those things. And in order to do that, you need to understand both preferences and the structure of behavior, right? So what are, you know, I can't interrupt, you know, Stuart now, so if the thing is guiding my phone and blocking calls, it needs to know I'm giving a talk right now, and therefore it can't interrupt me to take a call. It has to, whoever calls has to wait. So it needs to understand something about the structure of human behavior, the activities people are involved in, as well as your preference for an aisle seat or a window seat or, you know, 2 twin beds or a double bed or whatever it is you might want. Okay. So, so this is something that I think we're ready to start doing. I think the only part of this where we have to take a moral stand, right? So, as I said, we are not putting human values into machines. We're not, certainly not, you know, choosing one set of values that are right or anything resembling that. But there is a problem with people who have what we call negative altruism terms, right? Meaning that they, all other things being equal, they would rather have other people suffer than not suffer. Okay. Those preferences are problematic, right? You don't want, it seems to me that we don't want machines giving any weight to those types of preferences, even though they may be real, and I think there's a lot of evidence that they are real. So I'm willing to take a moral stand. I'm happy for philosophers to contradict me and say, no, you're not thinking about this right, but I think this is a place where we do have to take a moral stand and say robots are not supposed to help people cause suffering for others. So even if the person who has these negative altruism terms derives more happiness than he's causing unhappiness to other people, so to speak, right? I still don't think this is right. So another thing people ask about is, well, what if humans just behave badly, right? You know, what about the passport official who takes bribes, you know, to let people through in some developing country? Is the machine going to learn to behave badly because they're just watching people behave badly all the time? And I think the answer is no. Right? The machine is not learning to behave like people at all. Right? It's learning to understand what people want their lives to be like. The guy who's taking bribes doesn't want to be taking bribes. That's not his preference. His preference is to be able to feed his family and send his kids to school, and the government doesn't pay him enough to do that, so he takes bribes. Right? There's no reason why the machine has to do that. The machines would then understand, okay, I'll help the guy send his kids to school, and that way he doesn't have to take bribes. And so everyone will be happier. So there's no connection really between how humans behave and how a machine behaves that's trying to help humans achieve their preferences, because they operate under very different sets of constraints. And that's really important to understand. This other part, so the relativization of preferences means that this is part of the complicated structure of actual human preferences. So a naive utilitarian would say, okay, if you have a nice house that's worth such and such, if you have running water, if you have good health, that's 33 points. If you have lots of children, that's 80 points each. If you have, and so you kind of add it up. And this is, you often see these kinds of ways of guessing how happy and well-off people are. But in fact, it doesn't work like that. Right? The value of a nice house to somebody is actually far more determined by how nice his neighbor's house is than by how nice on some absolute scale his own house is. So this relativization of human preferences is really important. I think it's probably pretty unfortunate, right? It relates to this other thing, it relates to the negative altruism idea, right? So I'm happier than if my neighbor's house is considerably less nice than mine, right? Even though mine is not changing. And so that's an unfortunate aspect of human preference structure, and I'm not sure yet what to do about that, how to fold it into these considerations for how machines should behave. And then there are other complications with human preferences, which have to do with the fact that they don't fit the standard models of optimizing a sum of rewards. So all the work in reinforcement learning and sequential decision-making assumes that that your preferences can be explained by an additive reward function. That for each state that you pass through in the world, you can add up some reward that you obtain in those states. But experiments show that this is simply not true. So, for example, you can measure, so Danny Kahneman does a lot of these experiments, right? You can measure the pain that people experience. If I had a whiteboard, I could show you, but you can measure the pain that people experience during certain types of operations, right? And they can record how much pain they're feeling with a little clicker while this operation is going on. And so in one method A of doing the operation, the pain goes up and up and up and up, and then it goes down, down, and down, and down. Right? In method B of doing the operation, the pain goes up and up and up and up and up, and then it stops. So there's no pain in the second half of the operation. Now, which kind of operation do you think people prefer? It turns out that given a choice, okay, you've had both, and now we're going to do a third one, which one would you prefer? They'll choose the one with more pain, right, where there's pain throughout the operation, rather than the one where the pain stops halfway through. Go figure, right? But it's a fact. So it's no good pretending that it's not true or that they're irrational or anything like that. These are actual human preferences. And I think it has to do something to do with memory, right? What you remember of the pain, not just what you experienced at the time. And this leads then to complicated questions, right? Am I optimizing for the human now, or am I optimizing for the human in the future, looking back on the experience that I'm about to provide for them? And this is a really difficult philosophical question. Okay, so incoherence is also really important. So incoherence means that your preferences don't satisfy basic axioms that preferences have to satisfy, such as transitivity. Right, so if you prefer plain pizza to pineapple pizza, and you prefer pineapple pizza to sausage pizza, then you have to prefer plain pizza to sausage pizza. But what if you don't? Okay, well, then your preferences are not coherent. And in that case, there's simply no way that the machine can optimize your preferences. Right? Because whatever pizza the machine gives you, there's another kind of pizza that you prefer. Right? And you just go around in circles. You give it the plain, it'll say, no, I prefer the sausage. You give it sausage, say, no, I prefer the pineapple. You give it the pineapple, it says, no, I prefer the plane. Right? And this just goes on forever. There's no way to satisfy people with incoherent preferences. And probably our preferences are not coherent because our minds are made up of multiple subsystems that have different preference structures, and therefore and sort of compete with each other for control of our person. And so you're not necessarily going to see consistent behavior. Okay. And then the last point here, so I'm sorry I'm taking a long time, but these are all really, really important issues, not just for AI, but also for what is the meaning of effective altruism. The last point is about plastic preferences, right? So plastic preferences means preferences that are changed by experience. So you might think, okay, my ideal life consists of A followed by B followed by C. And then you experience A, and you say, you know what? I don't want B anymore. Right? Actually, I want D, E, and F. Okay? And so this is what we mean by plastic preferences. And of course, your preferences are plastic. Right? You're born with no real preferences to speak of, except, pain avoidance and sugar. Right? But you end up with these really complex preference structures. And of course, French preference structures are very different from American preference structures and all this stuff, right? So it's very culture-specific. It's very much a product of your environment, your upbringing, the preferences of other people, and so on. That's all great, except what is the machine supposed to be optimizing, right? Your preferences now for what you want your future life to be, or your preferences at the end of your life for what you wish your life had been. Right? Or some combination of these two. It's a really difficult question. From a practical point of view, we also have to avoid the situation where the machine can mold your preferences. In particular, can mold your preferences to make them easy to satisfy. Right? Which, of course, is what politicians do all the time. Right? They tell you that what you really, really want is this thing that they can easily deliver to you. This is one of the oldest tricks in the book. So this is a real problem because machines that are extremely intelligent could mold human preferences in all kinds of ways that we might a priori think are extremely undesirable. But we are malleable and we may go along with it at the time. Okay. So I think we're close to wrapping up. So I wanted to make a couple of remarks about the debate that's going on. So you probably see this in the paper, the debate between Elon Musk and Mark Zuckerberg, and it's becoming, I would think, what you might call a tribal debate, right? With the pro-technology camp and the anti-technology camp. So apparently, I'm in the anti-technology camp because I point to the fact that superintelligent systems may carry some risk for the human race. I completely reject this idea that this is an anti-technology view, right? I mean, any more than saying, a nuclear power station needs to have a safe containment system. That's not an anti-technology view, right? It's just common sense. Because if you don't have a safe containment system, your nuclear power station blows up like Chernobyl, and then the nuclear industry comes to a halt. Right? So if we want to have a successful AI industry, if we want to reap all those enormous benefits, then we have to take the risk seriously. And so having a tribal debate where people just strenuously deny risks, either from a kind of a defense mechanism or from straightforward corporate motivated cognition, right? This simple idea that if you're a company like IBM who has stake their future on AI, you go out of your way to deny that AI has any negative potential whatsoever, right? And so I'm seeing this over and over again in the debate, and I don't think this is helpful either. Just to give you an example of the nonsense that people come up with in defense, or what they think of as in defense of technology, right? So So Kevin Kelly, right, who's the founder of Wired, co-founder of Wired magazine, really intelligent bloke, many very insightful commentaries over the years on technology. His argument is that because intelligence is multidimensional, it's not on a linear scale, right? There are many aspects of intelligence, it's not a single number. Therefore, the whole notion that a machine could be smarter than a human is actually meaningless. Right? This is his claim. And so we have nothing to worry about. You think, so I asked my 12-year-old what he thought of this, and yeah, but if that was right, then gorillas wouldn't have anything to fear from humans, would they? Right? Because smarter than a gorilla is also meaningless. But clearly, gorillas have a lot to fear from humans, and they probably regret making us in the first place. Right? And so, the fact that very intelligent people, this is Rod Brooks, who's kind of a frenemy of mine at MIT, very famous robotics professor, goes along with this argument. But it's like this is so obviously a bogus argument. And then another one from Rod Brooks and Steven Pinker, who's also a brilliant guy, a very famous cognitive scientist, also at MIT. So maybe something going on at MIT. Right? So their view is that there's no possibility that intelligent systems would ever do anything wrong because they're intelligent. Right? And they will just recognize that they was wrong. Or that humans were really unhappy with what they were doing, and so they would stop. Right? But that sort of whole presupposes the solution to this control problem, that we build AI systems so that they're constitutionally unable to do things that make human beings unhappy. Now, I mean, that's a real, I think it's, as I hope I've indicated, a really non-trivial set of technical and scientific problems that we have to solve. And clearly, you can make intelligent systems that have any objective you want, including, explicitly having the objective of wiping out the human race. But many other objectives, like curing cancer, like fixing the environment, all of which would also lead to the elimination of the human race as a byproduct. Right? So it's clearly not the case that intelligence goes along with an intrinsic benign attitude to human beings. Right? The two are just completely orthogonal to each other. Okay, so to summarize, I think we can solve this problem, but it's far from easy. If we do solve it, then it has to become the standard for what we mean by AI, and it has to be, I would say, enforced. There have to be regulatory policy solutions to make sure that all AI systems are built according to the principles of provably safe, provably beneficial machines. And so eventually we won't need to say provably beneficial AI any more than we say bridges that don't fall down. Right? We just say bridges, and it's built into the meaning of the word that it's not supposed to fall down. It should be built into the meaning of AI that it's supposed to be for the benefit of human beings. And so, assuming that we do this, then I think the future can be extraordinarily wonderful. I think this could be the golden age for the human race. And I have a couple of concerns beyond solving the problem of provably beneficial AI. Right? So one is just, we call it the Dr. Evil problem. Right? So how do we know that Dr. Evil is going to use these provably beneficial AI designs and observe the safety rules of AI systems, right? Rather than just building some AI to take over the world. But I think another real problem is progressive enfeeblement, right? That if we have all these provably safe AI and everything's great, but as AI systems become more and more and more capable, we are likely to turn over more and more and more of the work involved in having a civilization to the machines. And for example, why would you spend 11 years in medical school to become a doctor when AI systems are going to be better at surgery than you? Right? Why would you ever bother learning mathematics when automated theorem provers are going to be better mathematicians than you are. Or in fact, it becomes a real problem. We've had no choice up to now but to carry on our civilization by teaching the next generation everything we know and hoping that they add to that. But AI, it can be a repository for our civilization. So instead of passing it on through generations of humans, we can now, or at least fairly soon, be able to pass it on through machines and have them run the civilization. And that's irreversible as far as I can tell. Right? And so I think this is a very serious concern. It's not a problem that AI can solve, it's a problem our culture has to solve. We have to be, I think, sort of eternally vigilant, almost kind of Spartan, in retaining the ability of humans to do things, to take on challenges, to learn, to sometimes fail, right? Not to have everything provided to them on a plate. Otherwise, our civilization may as well be over.